Hi everyone, welcome to the Arithmetic Zone. I know it's been a while since there's been a video on my end, but I'm back with a video going over the properties of triangles that you'll need to know for a Regents geometry or really just any high school geometry course. So when dealing with triangles, there's 6 basic types of triangles that are worth going over, and this is pretty basic stuff. So we're going to start with this isosceles triangle. And one of the hallmarks of an isosceles triangle is that it's going to have 2 equal sides with one side that isn't equal. And that's what these little marks show. These marks on the sides just mean that they're equal in measure. And these little arcs here just indicate that they have the same angle length as well. Now for scaling, the thing that makes scaling special is that all of the sides of the triangle are of different length. So if I were to trace over this triangle with some colors, this red side right here is going to be a different length than this pink side, which is going to be our largest side. And that's going to be different from this purple, which is going to be our smallest side. They're all different. Now for equilateral. As the name implies, it just means that all 3 sides are equal in measure, they're all identical, and that also means that all the angles within the equilateral triangle are equal as well. They're all going to have a measure of 60 degrees, and we'll talk about a bit why later. Now for the acute triangle. So before we go on to explain what an acute triangle is, I want to just note that this isosceles triangle and this acute triangle, it's the same image because this triangle specifically just so happens to be both isosceles and acute, but not all isosceles triangles are acute triangles, and not all acute triangles are isosceles. So I just want to get that little caveat before I go on. But an acute triangle basically just means that all of the angles within the triangle are acute angles, or that there are less than 90. It's important that all of them are less than 90 because when drawing a triangle, any triangle really, you're always going to have at least one acute angle. So all of them need to be acute for the triangle to be listed as acute. Now, moving on to the right triangle, you'll see that I have this little marking here, and that denotes a right angle, which is what a right triangle has. If it has a right angle, it's a right triangle. This 90-degree angle is super important, and it makes this right triangle one of the more special triangles because of how prevalent 90-degree angles are in math. Now, finally, we have the obtuse triangle, and you'll see I have this little marking here. It's an arc, and that denotes the obtuse angle or an angle that's greater than 90 degrees. So there are certain properties that all triangles share. It's obviously not just these 3, but these 3 are important. We'll go over the other ones a bit later. So we're going to check for the first condition. First, I want to just say that this figure is an equilateral triangle, but again, it works for any triangle. So the first condition states that the interior angles that make up a triangle add up to 180. So in an equilateral triangle, all of the angles have a measure of 60 degrees. So if I were to just label that on this figure here, 60, 60, and 60, if we were to just add those up right here, 60 plus 60 plus 60, we get that this is 180. We see that this holds true, and it'll hold true for any triangle. Now the second one, it talks about exterior angles, and exterior angles just means any angles that are formed on the outside of this triangle. Because these 60s are inside the triangle, they're interior. But if we want to see the exterior angles, we're going to have to extend or elongate the line segments that make up this triangle. So I'm going to do that here. Just going to stretch this out a little bit. I'm going to stretch it on this side too. And finally, we're going to stretch it out up here. So look like that. Now, in essence, what we've done is just elongate this straight line. And a straight line has 180 degrees. It's a 180-degree angle. And so I'm going to kind of just like box this area in green. In this green box that I made, there are 2 angles that make up this 180-degree angle. So we have 60 plus some unknown angle is equal to 180, and this unknown angle is going to be 120. So instead of this x here, I'm just going to write 120. And because all of the interior angles are the same, the exterior angles will also be the same. So this will be a 120-degree angle, and this is also 120 degrees. And now we're going to actually check what the second bullet point says. It says that all of the exterior angles that make up a triangle add up to 360. So if we just check that really quickly, we have 120 plus 120 plus 120, and we get 360, just as the bullet point says. And again, this will prove true for any triangle that exists. Now, finally, we have the exterior angle theorem, and I feel like this one is a bit more important than the last two, which is why it's highlighted. So it says that the measure of an exterior angle is equal to the sum of the two unrelated interior angles. So I want to focus on this word right here. First, I kind of just want to go over what is a related interior angle. So as we see in this box, these two angles are what form this straight line. So these two share an innate bond in making up the straight line, and they are related in some way. So let's just highlight this 120 right here. Let's just make this the exterior angle that the theorem is talking about. So because this 60 degrees is related, so to speak, to this 120, these two 60-degree angles are not. They're not near this 120, they don't touch it or anything. So what the theorem is saying is that if we were to add these two 60-degree angles, we should get back to this exterior angle. And lo and behold, if you do 60 plus 60, you do get 120. And again, this will hold true for any triangle that we have. So I have here some practice problems. These are Regents level practice problems, some multiple choice that you might see on a Regents geometry exam. So let's go over the first one. So we just want to find the measure of the largest angle in this triangle that's shown below. And we don't get any numbers. We have all of these angles in terms of x. So what we want to do is we want to add all of the angles in the triangle and set it equal to 180 because we know all of the interior angles have to add to 180 degrees. So let's do that right here. Okay, now we're going to simplify these terms. We're gonna clean up this left side. So we have 4x plus 16 is equal to 180. We're gonna subtract this 16 on both sides just to get rid of it. So we have 4x is equal to 164. You're gonna have a calculator during this test, so there's no need to go through the mental math, just put in your calculator. Divide 4 on both sides and we get that x is equal to 41. But that's actually not what the question is asking. It's asking for the measure of the largest angle. So this 41 won't actually be the answer. It's kind of like a trick. We have to test each of the angles. So I'm actually going to label the angles. We're going to say that this is angle A. I'm going to say that this is angle B. And this guy right here is angle C. So we're just going to pop in wherever we see an x for 41. So for A, we have 41 plus 15. And 41 plus 15 is 56. Angle B, it's just an x, so it's going to be a measure of 41. So that can't be the largest. And finally, for C, we have this 2 times 41 plus 1, and this is going to be equal to 83. And so because of that, our final answer is 483. Now for the second one, it gives us a bunch of angle measures of a triangle, but it doesn't actually like show us the triangle ABC. And this time we're only finding the value of x, not a specific angle measure. So with this one, when drawing a triangle, the way that the letters are shown is really important. So it says triangle ABC. Since this B is in the middle, the angle B has to be in between angle A and angle C when drawing it. So this is obviously going to be just a sketch. I don't know the specifics of the triangle, whether it's acute, obtuse, etc. I'm going to shimmy this down just a little bit. And we're going to say that this is angle A, angle B, and angle C, with angle B being sandwiched in between this A and C. Now we were given that angle A is x, angle B is 2x plus 2, and angle C is 3x plus 4. And we're basically going to do the same thing that we did with the first problem here, add up all of these interior angles and set it equal to 180, and do some algebra to get the value of x. So this is going to simplify to 6x plus 6 is equal to 180. We're going to subtract the 6 on both sides. We got 174 on the right. And if we divide by 6, we get x is equal to 29, which is 1. Now going back to the properties that all triangles share, this one is a relationship. It is the angle side relationship. And it says that the largest side of a triangle corresponds to its largest interior angle, and the smallest side of a triangle corresponds to its smallest interior angle. So I want to see how this looks like with the scalene triangle first. And I'm just going to draw over this triangle right here in different colors. We'll have that side be red. Let's switch it up. We're going to have this largest side be orange. And finally, we'll stick with the blue for our smallest side. So if it says that the largest side of a triangle corresponds to its largest interior angle, well, we have to spot where our largest interior angle is. Our largest side is the orange, but where's the largest interior angle? Well, it's going to be this obtuse guy right here. And our smallest angle is going to be this guy up here. And so the one in the middle, the one that corresponds to the red, is going to be right here. And so now we see a bit of a relationship. This red angle is directly opposite of the side length. The blue angle is directly opposite of the blue side length. And finally, the orange angle is directly opposite of the orange side length. So whatever's opposite of the largest side length is going to be the largest angle. Whatever's opposite of the smallest side length is going to be the smallest angle, etc. Now for this equilateral triangle, obviously all the sides are going to be the same. So I'm going to highlight this whole thing with pink. And then this pink corresponds to this angle. This pink side corresponds to this angle. And this pink side corresponds to this angle up here. And all of the angles are the same because all the side lengths are the same. Now, I specifically left out isosceles because isosceles triangles have their own theorem. It's kind of an extension of this angle-side relationship, and it's basically just stating that in an isosceles triangle, where the two sides of the triangle are congruent, the angles opposite to the congruent sides are also congruent. So basically, kind of like what we expanded on before, I'm going to draw over the side lengths, have these two congruent sides be the screen color. And then this opposite side, we're going to have it be pink. This pink side corresponds to this angle up top, the only angle that isn't equal to any of the other ones. And this green side corresponds to that, and this one over here. And just as shown in the diagram, these two angles are equivalent, just how these two sides are equivalent. Okay, so now we have some more practice problems. These ones are a bit trickier than the ones that we saw originally, but I think they are still very doable. So I'm going to let you read the question, and basically you want to establish a relationship between the different side lengths. So the first step we want to do is find all of the possible angles in this diagram. So first, I kind of want to focus my attention on this region here. we have an unknown angle here, and we know that that angle is supplementary to 115. So we can add it to 115, set it equal to 180, and then we just find what x is. If we were to subtract the 115 on both sides, we would see that x is equal to 65. So I'm going to erase this x and just put 65 here. And now we see that in this triangle, we have 1, 2, 3 angles. We have one unknown, but we know the other two. So we can do 70 plus 65 plus this unknown angle y is equal to 180. And then if we were to just simplify a little bit, we get 135 plus y is equal to 180. And we see that y is equal to 45. So I can kind of just erase this, then have it be 45. And now that we know all of the angle measures in the triangle, we can use the angle side relationship to determine the relationship between the triangle's side lengths, which is what the question is asking for. So first, I see that 70 is the biggest angle here. So I'm actually going to label in this little box right here, what is the greatest, what is the middle, and what is the least. What is the greatest side length value, what is the middle side length value, and what is the least side length value. So if I were to just take this 70, see what's across, directly opposite, we see that it's this line segment BC. That's going to be our greatest. The middle, this 65 is less than the 70, but greater than the 45, so it's going to be our middle. And so we're going to look directly opposite, and we see that this is AB. And the least is our 45. We look directly opposite, and we see that that is this side length AC. So establishing a relationship using these greater than or less than equal signs. We got AC, AB, BC. And now this is going to be the thing that governs which answer we choose. And from the looks of it, it looks like answer choice 4 is the one that aligns with what we are just established. Now the second one, this one has to do with a river, with surveyors marking locations along the river and the different angles that it makes up with angle ACB. When reading measures of angles in this way, you want to look at which letter comes in the middle. So in this case, it's C, because that's where the angle is formed. So ACB, we see that this is where the angle is formed. So this is angle 70. And the measure of ABC, the angle is formed here. So this is 65. And we're asked to find the relationships between the triangles. So again, you kind of want to find this angle BAC. So we're going to denote this with an X. So it would be 65 plus 70 plus X is equal to 180. And X is equal to 45. This is actually a very similar triangle to the one that we had in the last question. And then from here, we would use the angle side relationship again to determine which one's the greatest, the middle of the line, and the least. I'm going to write that up here, greatest, middle, least. Our greatest is again the 70, so we're going to just take the 70, pop it over to the opposite side, and we see that this is measure AB. Our middle guy is this 65, so in a different color, I'm just going to go over, pop it to the other side, and we see that this is measure AC. And our least is going to be this 45 again, and we see that this is measure BC. And then we just go over to our answer choices, see which one aligns, and we see that this is answer choice 3, because BC is our least, AC is our middle, and AB is our greatest. Great. So now we have the Pythagorean theorem, probably one of the most famous math formulas like ever. So I have the definition there, and I want to just label this triangle really quickly with this side. Let's just label this A. Let's label this guy B, and then this largest side C. Honestly, it doesn't matter which one is designated as A or B. You can honestly switch them, but this hypotenuse, the largest side of the right triangle, always has to be C. And so we have this formula, a squared plus b squared equals c squared, where c is the hypotenuse. And with this triangle, the relationship of that relationship will always hold true. And actually, any set of three numbers, three positive numbers, that satisfies this formula right here are known as Pythagorean triplets. Probably the most famous set of three numbers that satisfies this formula is 3, 4, 5. It's known as the 3, 4, 5 right triangle, and that's probably the most famous Pythagorean triplet. So again, we'll have some practice problems to kind of just test the knowledge of, or rather test comfortability with the formula. So we have this right triangle here, and we know it's a right triangle because we're given the measure of this triangle or this angle to be 90, and a 90-degree angle is a right triangle. So the Pythagorean theorem applies. So I'm just going to write out our a squared plus b squared is equal to c squared. And I'm going to label the triangle that we have right here with AD being, AD having a measure of 5 root 2, AB having a measure of 2 root 15, and then this BD part, which is what we're trying to find, is unknown. So C has to be this value. It can't be, it has to be on the right side of the equation no matter what. So let's just fill in what we know. X squared plus 5 root 2 squared is going to be equal to 2 root 15 squared. And you can just distribute this exponent into the different multiplication, or into the different multipliers, excuse me. We have x squared plus 25 times 2, I'm going to bracket this off, is equal to 4 times 15. Simplifying this further, we get x squared plus 50 is equal to 60. Then we get, if you were to subtract the 50 over on both sides, we get x squared is equal to 10, and then undo that exponent with the square root, and we get that x is equal to the square root of 10, which is answer choice 1. Now, we have this word problem again. I like to incorporate problems that aren't just like the first question where it's just giving you a triangle, it gives you a little scenario, because these are like the more common types of questions. But I don't think this one is that bad either. So you want to know the distance between the two poles. You want to know this value, that's our unknown, and that's our hypotenuse C. So again, we have this a squared plus b squared is equal to c squared. We're going to have 75 squared plus 30 squared is equal to x squared. And again, you have your calculator. So this left side is going to be equal to 6,525, all equal to x squared. And we're going to take the square root of both sides, kind of to undo that x. And then you get that x is approximately equal to 81, which is 2. Great. Now we have the triangle inequality theorem. So I'm going to give you a chance to read the chunk of text above, but I'm going to break it down here. So when I talk about the sum of any given pair of side lengths of the triangle being strictly greater than the side length of the third, I'm going to visualize this, excuse me, by again, just kind of tracing over this triangle with different colors of my pen. Oh, excuse me. So the largest side length of this triangle is C. And I want to prove to you that A plus B, the side length A plus the side length B is going to be greater than C. So I'm actually going to copy this little red line segment, and I'm going to make it vertical. It's going to cover the text a little bit, but I think that this is a good way to kind of just visualize what I'm saying in that large chunk of text. So A plus B, I'm basically just going to put these two line segments together. Well, try at least. Oh, whoops. Okay. Okay, that's kind of as, maybe I should do it vertical because it'll fit better. Yeah, vertical seems better. Okay, just some trial and error. So that's going to be our a plus b. And if we were to put this right alongside this pink guy, we can see that a plus b is going to be bigger than the pink, very marginally, but it is bigger than the pink. And I want to acknowledge why this is so important, because let's say that this c term was greater than the value of a plus b. So let me just make a new line, green, that's even bigger than this side length. Now, if I were to take the measures of a and b and try to form a triangle, it's going to be pretty difficult too, because this guy is kind of super large. If I were to take this value of a and I place it right here, and this value of b, place it right here on the other end, there's no way that they meet. I can try to make a be a little steeper. Let's see if this will work. And I can try to make b be a little steeper as well. But no, there's just no way that this red and blue line can close the gap to this enormous green. So this is why a plus b has to be greater than c. And it's the same way for each of the other line segments with these inequalities shown. And a plus b can't be equal to c either, because if we had a plus b be equal to c, then it would kind of just be like two line segments on top of one another. I'll show you what I mean. We'll take this a, we'll do it, horizontal again. Excuse me, I have to there's not a lot of room on this slide. I probably should have made more, but trial and error. Okay, we're gonna have this a plus c conglomerate again, and I'm gonna make more space here. Let's say that the third side length of this triangle was equal to this. So basically just an exact carbon copy with a plus b being equal to c. There is, if I were to move this over here, there's no way to make a triangle out of this. Because, well, I just moved that little blue line with me, I apologize. But you see, there's no way to make a triangle out of it. It's just gonna be two straight lines on top of one another. So it has to be strictly greater. And additionally, the smallest side length of the triangle cannot be less than the difference between the two larger side lengths, because it's almost as if you have negative length at that point, and that just doesn't make sense in terms of it just doesn't make sense to have a negative length. So that's basically what I'm getting at with this triangle inequality theorem. I think it'll be better if I were to show it in practice with a practice problem. So I'm gonna let you again read the question. It's about the scenario with Elma wanting to take a specific path and wanting to know if she will have to hike farther than 6 miles. So this is a triangle, and again, we can label these side lengths with A, B, and C, with C being our greatest. And because we know that A plus B has to be greater than C, and if she's taking this path right here, she is going to have to travel more than 6 miles because of the triangle inequality theorem. So just making a quick explanation, we're going to say yes, because the sum of the two side lengths of a triangle will always be greater than the third unrelated side. That's kind of like the more technical way to say it, the more math fancy way. So now we'll move on to the second question. So it states that the length of two sides of a triangle are 7 and 11. So just reading that, I should draw out this triangle. This is a sketch. Obviously, we don't know what the triangle is, and obviously not drawn to scale, it's a sketch. So we're going to say that this is side length 7 and 11, and which inequality represents all possible values for x the length of the third side of the triangle. Okay, so we don't know what this is. We're not even asked to find a specific value, just what it could be. So we know that this x value has to be less than the sum of 7 and 11. So 7 plus 11 has to be greater than x. So 18 has to be greater than x. We can actually just eliminate both 1 and 2 because we're never going to have those equal signs for pointing towards the 18. And in a similar vein, a minus b can't be less than c. So 11 minus 7 has to be less than x. So 4 is less than x. And this is going to be answer choice 4. You don't ever want to use the greater than or equal to or the less than or equal to sign for, I might have gotten those mixed up, but the point is you don't want those equal signs whenever you're establishing an inequality with triangles. It has to either be strictly greater than or strictly less than. Okay, now for the side splitter theorem. So I'm going to read it out to you. I feel like this is one of those things where it's more intuitive, where we have an example. So it states that if there is a line segment that is parallel to one of the sides of a triangle and it intersects the other two sides of the triangle, then the two sides of the triangle will be split proportionally. So that's just the fancy definition. And the biggest thing about the side splitter theorem is the proportionality and that the lines are parallel. So I'm actually going to write this out. A proportion is really just a fraction, and vice versa. So the fraction 1/2 is really just the same thing as saying a 1:2 proportion. So knowing that, we're going to look at this quick example. I put the triangle not drawn to scale, little disclaimer there, but we're going to find the value of this unknown sine length using the side splitter theorem. And I'm just realizing I should have said that the line segments are parallel. I guess we're just going to assume that it is since the side splitter theorem applies. These two should be parallel. And so now that we know that proportions refer to fractions, we have to make sure our fractions are accurate. So we have to do something like, or rather, here we go, or I can erase that. When looking at this triangle, we see that we have this small area right here, and we have some big area, and we're trying to find this unknown x. This 3 and 5 pertain to our small area, and this 7 and the unknown x pertain to our big area. So when we are making our fraction, we have to make it so that we have a small piece of line segment from either the left or right over a big piece of line segment be equal to the same small over big on the other side. Let's just make this our left side and our right side. So on the left side, our small segment is going to be this 3, and our big segment is going to be this 7. And this is going to be equal to the small segment on the right side, which is going to be our 5, and our big segment is this x. Now we have our proportion, we have an equation with one unknown, and we can solve this. So we're going to cross multiply. We're going to have 3x be equal to 35. And again, just doing this on a calculator, you get that x is approximately equal to 11.67. And that's how you would find an unknown side length using the side splitter theorem. Now, the triangle midsegment theorem, I'm going to, again, let you read it, but it's really just an extension of the side splitter theorem. It's a special case, if you will. It's just that you still need to have this line segment be parallel to the other third unrelated side. So I'm going to just note that there with my little arrows. But the proportion or the fraction will always be 1:2. So on this triangle, I'm going to make up some side lengths. We're going to say that this is 2, this is 4, this is 6, and then this is just going to be some x. And we're going to find the value of x. We're going to do the same thing. Small over big is equal to small over big. So we have 2 over 4 is equal to x over 6. which is also equal to 1/2 because the proportion will always be half its length. So we get that x is equal to 3. And that's really it. The triangle midsegment theorem is kind of just a very special case of the side splitter theorem. And that's really all that there is to this. So now for these practice problems. So for the first one, we're given 2 line segments and we need to find the value of x, not the value of any particular line segment. So because BD, this line BD, connects these midpoints, B and D, of the triangle, it has to be parallel to AE, and it has to be half its length from the triangle midsegment theorem. So we're just going to make this parallel, and we know that 2 times BD is going to be equal to AE. And we know that BD is equal, they give us the equations for BD and AE. I'm just going to write it out. 2 times 7/2 x plus 2 is equal to 3x plus 6. And now from here, we just use algebra to find this unknown x. So distributing this 2 and we get 7x plus 4 is equal to 3x plus 6. I'm going to subtract the 4 on both sides and this 3x on both sides. We get 4x is equal to 2, and that x is equal to 1/2, which is B. Now for the second question, this is going to be more side splitter theorem, not the triangle midsegment theorem. I'm going to give you a chance to just kind of read that. And I'm actually going to label really quickly. So this length is going to, rather, I'm going to shrink this just so that it doesn't get in the way. The CL is going to be 3.5. LE is going to be 7.5. EA is going to be 9.5. And this is parallel, so we can use the sentence of the side splitter theorem. So we need to find this length AR to the nearest tenth. So we're going to set up our fractions with small over big. You could do big over small, but I'm just kind of more accustomed to small over big. The left side is equal to small over big on the right side. So on the left side, we have 3.5 over 7.5. Our small over big is equal to x over 9.5. So now we would just cross multiply. We get that this is like 33.25 is equal to 7.5x. And if you were to divide the x out on both sides, you get that x is about 4.4. You get like 4.43 repeating. So just like approximately to the nearest tenth, that's going to be Q. Now we're going to move on to something different. We're going to go over what a median is. But before we can talk about the median, we have to talk about what a vertex is. So a vertex, very simply, is just the intersection point between 2 different sides of a triangle. So on this triangle right here, if I were to draw out this side of the triangle and this guy right here, where this pink and red line meet right here, I'm going to label it in blue. This is a vertex. It's basically like these points of the triangle. And every triangle will have 3 vertexes. We have one there, we have one up here, and we have one down here. And so a median is going to be a line segment that connects this vertex, one of these 3 points, to the midpoint of the opposite side of the triangle. So that's what this black line is here that we have in the middle of the triangle. This is a median, and it's going to divide this side of the triangle into 2 equal parts, and it's actually going to well, rather, I'll say that for later. Every triangle actually has 3 medians because it has 3 vertexes. So we can draw a median down here, and we can draw a median from this blue point up here. It should be obviously not drawn to scale. Like drawing a median, you would normally use a compass, and I don't have that right now, but this is what a median is, and it actually will divide the triangle into however many parts there are medians. So if there's 1 median, there will be 2 equal parts. It's like 2 to 1 ratio. If there's 2 medians, the triangle will be split into 4 equal parts. And if there's 3 medians, the triangle will be split into 6 equal parts. Again, my drawings don't do it justice, but just know that a median does divide a triangle cleanly into 2 identical triangles. And that's kind of what I just talked about here. The median serves as the bisector that splits the opposite side of the triangle into 2 equal parts, and the median will divide the original triangle into 2 congruent triangles. Now for the altitude. An altitude is a line segment that connects the vertex of a triangle to the opposite side length, and it always forms a perpendicular angle with an opposite side. So this line right here will make 2 perpendicular angles here. And that's really important when you have just some triangle, because right triangles are really important and easy to work with the Pythagorean theorem and stuff like that. So it is a very useful tool to kind of just make altitudes to kind of learn more about a triangle. So there are some key distinctions between the median and the altitude. So not all medians will form this 90-degree angle with the opposite side lengths, and not all altitudes will bisect the opposite side length. In this diagram, this side is very clearly smaller than this side right here. But there are line segments that do fall into both a median and an altitude, and we call those perpendicular bisectors. So here's just a practice problem. We only have the one because this one there's like a lot going on. I'll let you read the question right here. But before I go into this, I kind of just want to say, you want to make a collection of everything that is known and see if it corresponds with any of the answer choices. So going through this one by one, we're given this triangle ABC with base that. We have median BF. Okay, so we're going to pause and kind of just focus on this median part. So if this guy right here is our median, we know that it's going to bisect the line segment that it goes through. So this part of the triangle, I could have drawn that better. This side of the triangle is going to be equal to this part of the triangle. So I'm actually going to write that right now. AF, this whole thing, is going to be equal to FC, or congruent, let's say. Okay, so let's see if that kind of aligns with anything that we have here. And we actually see that that's answer choice 4. CF is going to be congruent to FA. They just kind of swapped around the letters, but it doesn't matter. And that actually was not as bad as we thought. We didn't have to use anything with altitudes and this bisector, angle bisector. We just had to go through what we're given and see if it corresponds. And this time we got lucky. It just happened to be the first time, but I do think it's a good way to kind of just organize your thoughts, because there are problems like this that put in unnecessary filler information to confuse you. So now we're going to go over how to find different centers of a triangle. So there are 4 different ways to do it. They're all different centers. They're technically called points of concurrency, but I digress. So to actually find these centers, you would need a compass, like if you were to draw it out. And I don't have a compass again, so that can't be demonstrated. I can try my best, but they obviously won't be drawn to scale. So first we have this centroid. And so we're going to read it. It is the point at which the 3 different medians of a triangle intersect. So in this image, this point right here is going to be our centroid. This is kind of like the center of mass of a triangle. Not to get all physicsy, but it is that. And a centroid has this special property where I'm actually going to draw out this. I'm going to highlight this specific median, but it works for any median. If you take any median that makes up a centroid, it's going to be split by the centroid with a proportion of 1 to 2. Basically, what this is saying, if this side length right here is some length x, I'm going to do that in a different color. If this right here is some length x, then this guy up here is going to be double that, 2x. And that's really important. That holds true for any median that you take of the centroid. And if you want to look at how they stand in reference to the whole median, this whole median is made up of an x and a 2x. So it's going to have an overall measure of 3x. So So this guy right here is kind of like 1/3 of the median. And this guy right here is 2/3 of the median, if you kind of want to look at it like that. So now the incenter, or not the orthocenter, my apologies. So this is going to be the point at which the three different altitudes of a triangle intersect. So again, to the best of my ability, I tried to draw the orthocenter. It'll be this point right here. Again, like this should be drawn with the compass, and I can't show you how to do that today. But all of these lines are going to form 90-degree angles with their respective side lines. So this is a 90-degree angle right here. This is 90 degrees, and this is 90 degrees. And I know like here, like this doesn't really look like the center of a triangle. It's kind of like all the way out here. But for different triangles, it'll be better at producing this kind of center. Like with this triangle, it doesn't, but there are definitely other cases where the orthocenter will work better and look more like a traditional center of a triangle. So now we have the incenter. So this I don't have drawn because this should be drawn with a compass. I'm going to keep repeating that because these are all going to look slightly different except for the circumcenter. So this incenter is going to be a point at which the three different angle bisectors of a triangle intersect. So I kind of briefly touched upon angle bisectors, but basically an angle bisector is going to be a line segment that goes through an angle and cleanly splits it in two. I'm going to try my best here. I don't think that looks. I'm going to try again. Again, no matter how well I think I do this, it's not going to come out the best, but okay. So this line segment right here is going to split this angle, this top angle, into two pieces of equal length. So this is going to be x and x. I'm going to try and draw one over here too, kind of see where it cleanly, yeah, that looks fine. And finally, the one here, going to go from our vertex, see where it intersects right there. Yeah, that's good. And all these three line segments that serve as the angle bisectors should intersect at one point, which serves as our incenter. Same thing for the centroid and orthocenter. All of the medians and all of the altitudes of the triangle should intersect at one point. And if it doesn't, it might just be due to human error. So, but they do intersect. Now, finally, for the circumcenter. So before I go on with this image has a lot going on. This is kind of like how you do the actual construction. This image is from Wikipedia because this one, the circumcenter, is actually really hard to draw without a compass. Like I could kind of do the incenter. Yeah, I'm not even going to try the circumcenter. So the circumcenter has to deal with the intersection points of these three perpendicular bisectors. A perpendicular bisector has the properties of both a median and an altitude. It'll split the opposite side length into two equal parts and form these right angles. So in this case right here, this point right here where the pink is going to be where the circumcenter is. And just like with the centroids, it's going to create 6 identical triangles because it's going to bisect the lines opposite. So I'm going to go in with a highlighter. This triangle is going to have the same value as this one, same as this, this, and this. It doesn't look like it in the picture. I'm actually not too sure why, but that is how, those are the properties of a circumcenter. Those are kind of like the 4 different centers of a triangle that are most tested in Regents geometry. I'm not sure that there's another one. So yeah, there's that. Now we go on to our last 2 practice problems. These ones are actually kind of tough. So I'm gonna let you digest the first one, and I'm just gonna label what we have. So we have this angle FEC, the guy up here, up top. This whole thing is gonna be 84, like the whole thing, not just one part of the angle. And ECF, this whole thing is going to be equal to 28. And we want to find BRC, which is right here. So because point B is the incenter, if we go back, you see that incenters have to deal with angle bisectors. So if this is the incenter, excuse me, we know that this line ER bisects 84 evenly. So what this tells me is that this angle right here is equal to 42, and this angle right here is also equal to 42, because a bisector kind of cleanly cuts it in half. So I'm actually going to focus on this triangle ERC for just for a minute. I'm going to do my best to recreate it. It's a sketch, so okay, that's fine. So this is point E, this is R, and this is C. So the angle REC is going to be equal to 42, given to us by our knowledge of the incenter and angle bisectors. Angle ERC is unknown. This is what we're trying to look for. And angle ECR is equal to, well, if we look at this, I'm going to go in with my, actually, I'll just go in with my laser pointer. This line also goes through point B, which means it's also an angle bisector that makes up the incenter, which is this point B. So it's going to also cleanly divide this angle, but we actually don't need to find it because this is going to be an angle of 14, but we're focusing on this whole thing of ECF, or ECR, sorry, we're stopping right here. So we're going to use this whole angle 28 instead of bisecting it into its component of 14. We're just going to leave this as 28. And now we have the three interior angles of a triangle, and we know that those all add up to 180. So we're just going to have 42 plus 28, excuse me, plus x is equal to 180. So cleaning this up a little bit, we get 70 plus x is equal to 180. And finally, we get x is equal to 110, and that is BRC. I labeled it as ERC, but right here, this would be the point B. So it still holds that it is B, excuse me. It still holds that it's this BRC guy. And finally, our last practice question. So we have this triangle with medians intersecting. So this is going to be our centroid. And we're going to look at which statement must always be true. And this is kind of like where this idea of the different proportions of a centroid come into place, because it's dealing with the relationships between the two. So I'm going to focus on this line. I'm going to highlight it, SMC. Okay, I'm actually going to just redraw it right here. M is our median. We have S, and we have C. And if we remember, this is going to be split 2 to 1. So we're going to have this be some value x, and this is going to be double that. And there are 3 total parts to this line segment, so this whole thing is going to be equal to 3x. So MC is going to be 1/3 of the whole line segment SC. And writing this out in math terms, MC over SC is 1 to 3. If we were to cross multiply, we get 3 times MC is equal to SC, and we get that that is answer choice 1. And so that's it for me today. That's all there is for the properties of triangles that you need to know for Regents geometry course. It is a lot, but I'm happy to say that up next is finally this geometric proofs part 2. I made the first geometric proofs video maybe like a month ago. It has to be more than then by now, but now I feel like with this triangle knowledge that we went over, we are finally ready to go into the world of triangle proofs, which can get tricky fast, but they are all very doable with the right mindset. So I hope you'll join me, and I'll see you guys soon.